by the way, just to kind of remind everybody, this public hangout thing, asking for RSVPs by September 4th, which is like what, next Saturday? Like a week from Saturday, something, or September 5th, sorry. So, yeah, let's try to get out the word as much as we can. And I at this point, I'm not sure we will really have much of a chance to get out beyond the membership, but let's really try to see if we can get members out there. Emphasize the fact that there's going to be food. That always attracts people. So.
Wes, what do you bring besides dogs? Are you doing potato salad, beans?
I was gonna buy potato salad and macaroni salad, and beans. Yeah, I was gonna get beans. But then, you know,
So-
tin cans.
Yes.
Beans and,
Yeah.
I think we-
use a regular buns. I'm not gonna worry about the buns.
And I think we were also thinking about some kind of a dessert type of item.
Oh, because I was gonna get one of them big trays of cookies.
Okay. I think maybe Laura was thinking perhaps some form of pie, or she makes this pumpkin bread stuff that's
Oh yeah,
good.
that's
So,
all it worked. That all worked.
so anyway, that's probably what we'll do. Probably wouldn't be a bad idea for people to kind of circulate their plans so we don't end up with, too many of one thing and not enough of another. Anyway, I hope that we'll see some people there. Like I
I've
said,
got the condiments already.
okay. So there's that. Anybody gonna watch this tonight? If there's, looks like it'll be pretty clear out
Yeah.
actually.
With a shirt, I mean,
I'm going to.
Yeah.
For my front step.
If I'm still awake at that time, which I think is probably about a crapshoot, coin toss. Like I said, I had to go up yesterday. I had to go all the way to Des Moines to get my car. So anyway, after work. So anyway, this is kind of the prime time for this. It's actually not super late when it'll start.
No, it's
so.
not.
I'm going to be hopefully watching it from the deck of the house in Shawnee, which may or may not work. But anyway, we're in the area where it should
I
be.
don't think it gets total here.
I don't think it gets
no,
total
it's like
anywhere, does it?
97% or something.
Yeah. They said it would be not quite a blood moon, which
Yeah.
take that for whatever it's worth. But
Mhm.
I don't know. I think these things are pretty cool. So.
You could look on either side of that full moon with that's total. Look on either side of that, that's probably about what you're gonna see.
About one of these, yeah,
Yeah.
yeah. So, should be a good show though. So
Yeah.
It's not gonna cover. Mhm.
here is a piece of news. Did you all realize this?
Yeah, I saw
Monday
that.
this past week was 20th anniversary of the vote by the American Astronomical, or whatever it's called, the International Astronomical Union, to
Mhm.
officially demote. Well, again, I hate to use the word demote because that's really not what happened, but they redefined what a planet was. And this is actually going to bear a little bit on what I want to talk about a little later tonight. And Pluto became
They
a.
actually put the description back to where Tom Ball set the telegraph, saying it was a trans-Neptunian object.
Yeah.
Mhm.
So anyway, it's been a subject of lively debate ever since then. There's now these rather entrenched, and in some cases really not just, I've been involved in science research for 40-ish years now, and I've seen people disagree with each other, and in some cases rather heatedly, but then they all, everybody goes and has a beer afterwards,
Yeah.
and it's just like, I think that some of it is actually getting rather personally nasty. In
It's
particular,
almost like politics.
yeah, it's almost like it's politics.
Maybe that is.
One of the major kind of debaters in all this are Michael Brown, right?
Yeah.
Mhm.
Who is an astronomer and is in the camp that wants to see planets defined astronomically, which is the current way. So those rules about,
Mhm.
got to be
Now it's orbit.
equilibrium, got to clear your orbit, got to be orbiting the sun. That's astronomy. Then the sort of geophysical definition, which is really just if you have enough gravity to be a sphere, you're a planet, which also includes everything we call a moon.
Mhm.
One of the leaders of that is this guy named Alan Stern, who is, I believe, at the Space Telescope. He was at Colorado when a student there. So anyway, and these guys have this debate on YouTube you can go look at. And this gets kind of nasty. I mean, I was really rather taken aback by how, at first I thought these is just symbolism, they're kind of shooting at each other. No, it seems like they really don't like each other. And it's weird to me, but anyway. So, yep, this was Monday that this happened. This is something that's coming
Yeah.
up. This is actually not the correct, when I screen grabbed this, it was a couple days ago. So if you go look at the current time, 2 hours, 11 minutes until they launched the Nancy Grace Roman Space Telescope, the latest in the NASA space telescope, large space telescope constellation. It's kind of an interesting story behind this thing. Optically, it's much more similar to the Hubble in terms of size as well. About a 2.5 meter mirror, 2.4 meter mirror. Its cameras are optimized for shorter wavelengths than the Webb. The Webb, right, is its main camera is huge. It's the size of a tennis court, and its cameras are optimized for far wavelengths because it's designed to pick up things that are deeply redshifted, right? So they're shifted way up into the spectrum. This thing it's optically more similar. Its cameras are optically more similar to what's on the Hubble Space Telescope, except the Hubble is a relatively narrow field of view, and this thing is super wide field of view. At least one of its cameras is. This is also going to be put out into one of the Lagrange points, so unlike the Hubble, which is really an Earth orbit, this thing's going to be out a little bit more distant. It's mainly designed to, one of the major things that it's designed to look for is evidence of dark matter, but it's also going to have a pretty significant role in finding exoplanets. Its wide field camera is actually a monitor camera. It's instead of pointing it at an object, you just point it out in space and it collects. And it's going to look at the galactic bulge and see if it can find evidence of gravity winds and planetary stuff. So it's all pretty interesting. And it also has a much more narrow camera, much more narrow field camera, which is in the optical near infrared wavelengths, visible light, just beyond visible light. And it has a spectrograph associated with it, and it's designed to look for evidence of biochemistry or geochemistry in exoplanet atmospheres. So those things are going to be pretty cool. It actually, the story I heard is that its origin was that the National Reconnaissance Office, which is the kind of bland name for the satellite spy people, they launched a whole series of new spy satellites, and they decided we don't need a couple of these. God almighty, these things must cost billions of dollars. And they thought, we got a couple of them, we don't need them. You guys want NASA, you want it. And so they gave it, this happened, I don't know, 10, 15 years ago, I guess. They gifted a couple of these unused spy satellites to, of course, stripped of all the cool stuff, right? And so NASA built the thing was originally called the Wide Field Infrared Telescope. That's not a very inspiring name. So it ended up being named after Nancy Grace Roman, who was the mother, if you will, of the Hubble. She was the one who led the team that developed the Hubble. So very appropriate that the next generation is going to be named for her. So anyway, this thing's going to be put in orbit later this week. You never know with launching things into space, and should be interesting. Should be a very good show. It's going to be launched by one of these super heavy rockets, which I had a chance to see one get launched summer before last. Quite a sight. So anyway, so there's that. Also, I wanted to update you guys on dark sky, and I think we talked a bit about this at the last meeting. We all know the deal, right? Light pollution is getting worse and worse, and to make matters even worse, now there's this, I won't even use the words that come to mind, idea that we're going to put these people who are bad are going to put these mirrors in orbit, right? This reflect orbital thing.
Mhm.
They've actually cleared the way for the first test article of this to be launched. This thing is huge, by the way. It's the size of the mirror is about 60 by 60 feet. So to put that in perspective, a tennis court is 78 feet long and 36 feet wide. So it's about 1.5 times the area of a tennis court. These things are big. And they're going to put the first one in orbit. The FCC cleared it. Apparently, the only government entity that would have anything to say about this is the Federal Communications Commission. And their take on all this is, I don't know, as long as you're not blocking radio frequencies, it's not our problem. So there's no other organization that has anything to say about this. So this thing is scheduled to be launched. In orbit, the idea behind this is that it's supposed to reflect light down. You can like run a solar panel at night, which apparently it will be over an area about roughly 3 square miles, kind of like a full moon. So not like daylight. So, you know, how much actual electricity you're going to get out of that seems questionable to me. The other thing they talk about is, well, you know, if somebody falls off a cruise ship in the middle of the Pacific and there's no light out there to look for them, we can point this thing, which, I mean, that's a great idea, but I think there's better ways of doing it than, anyway.
Well, the thing that, reading about this that I haven't heard, I'm surprised I haven't read more about it, is just that, they know that the human mind, body, etc., has to have some dark.
Animals too. I mean,
Animals
I mean,
too. I know, and they're just, it's like, doesn't anybody care or what the heck?
Well-
It's like they just kind of blew over that altogether.
well, and you know,
And-
the impacts on astronomy will probably be among the least. And I mean, obviously that's
Yeah.
important to us, but
Uh-huh.
you know, the disruption that this could cause. And the eventual plan is to put about 30 to 50,000 of these in
Uh-huh.
orbit. This would look a bit like, even if it wasn't pointed at you, it would look a bit like Venus in the night sky. So imagine 30 to 50,000 Venuses orbiting the Earth. And then there's this other asinine plan to, now there's going to be advertisement. So the
Yeah.
first advertiser that's going to launch in orbit is McDonald's. So there's going to be a McDonald's ad. And then just today I was listening to a podcast where there's a company that now wants, it's Elon Musk, of course, who wants to manufacture these orbital data centers. He could be as many as 1,000,000 of these things. He wants to build a factory on the moon that will manufacture these things automatically, right, robotically, and then shoot them off with a railgun into Earth orbit. So now we're talking about perhaps 1,000,000. This is, I mean, and to me, it's just like, this has got to stop. But anyway, the reason why I mentioned this is that one of the organizations that's strongly leading the opposition is the Dark Sky International, which some of us, Jerry, you are a member, right? And perhaps some of the other of you as well. I've been in touch with Rick from AAL, who's not here tonight, but also a member, also one of our members. And I got in touch with the chairman of the board of the Lake Afton Club, which is the Wichita Club, about maybe getting a chapter of Dark Sky International here, maybe in eastern Kansas. There's a chapter in Missouri. There's a chapter in Nebraska, southern Nebraska. And it could just be a way to, help a little bit with this. Now, there is some issues with it. It does require a commitment. They expect outreach, they expect education. In order to apply, you have to have a certain core of members who I actually have not been a member long enough to qualify for this. So it would be a fairly steep commitment, but I just wanted to kind of gauge people's thoughts. I mean, is this something we want to try to pursue?
A week ago, I did talk to the Sierra Club, Sperryville, on Dark Skies, on Life, and that system came up pretty prevalently.
I mean, it's.
I mean, it's just the thing that, when I read it, I first thought they got, but they don't, I mean, just from a medical standpoint, are you kidding me?
Yeah.
I mean, humanity was never made for that. and they wanna light everything up like that. It's just so stupid.
Well, and I personally think that it's, I don't know. But here's the thing, the people that are trying to do this have a ton of capital available to them. This is not a shoestring startup. These people are already building hardware and clean
And
rooms.
if you go to look on their website, I dare you to find anybody that's over 55.
Yeah, they're all just a bunch of, young pups.
Well, and it's one of the things too, that I don't remember where I first saw about this, but, I mean, if you ask people out and let them think about it, nobody's gonna want this damn thing.
Well, I don't know. I mean, maybe
You
there
know?
are, maybe there is a constituency that would let me, maybe super wealthy people who can afford this
This is driven
wouldn't
by,
mind have it pointed at their
Oh, yeah.
backyard for some.
it's driven by money, it's not driven
Mhm.
by anybody's desire to do good.
Well,
But it-
yeah,
it
and
seems
the
great.
thing, that's just the thing, when you've got money like that, you get up there and do it, and by the time people realize what's going on, it's too damn late.
Yeah. Well, that's the thing. Once any of these are actually in orbit, then the genie is out of the bottle because you cannot get them back. So,
Yeah. Later.
well, I suppose you could. That's the thing, is there is no international body that governs space. There are a few treaties that are essentially
Maybe
the
by-
same treaty that does the Antarctica,
Yeah.
how you is theoretically applies in space, but the Chinese are attempting to land probes on the moon that are probably there. They're going to be looking to mine and stuff. It's going to turn into worse than the Wild West. And so anyway, I just was wanting to get your thoughts. Is this something we want to maybe try to pursue? Is anybody interested
You
in
mean joining it?
trying to get a chapter?
International.
Yeah, trying to get a chapter. I don't know. I mean, obviously, I'm not going to ask for a show of hands or volunteers or anything right now. I just want to kind of plant the idea that maybe this is something. I know when I was at the Astro League regional meeting, Misral meeting this past June. I think the chapter from Oklahoma little booth set up. So anyway, it's just a little update on all that. That's a bit. So I've been kind of thinking about what to do with these focus sections, and again, I always want to try to see what we can do to make the meetings a little bit more, I don't know, interesting or fun. We had been doing, or for a while, I'd been doing constellations, but I sort of ran out of gas on that. I hope to kind of circle back to that. So this is one that, August is a big month for meteors, and so this is one actually that I've done before. So if you think you've seen this before, you're probably right. But I figured I would kind of throw this out there. Also, again, and my apologies for this, time has not been on my side for the last, I don't know, about 3 months now. So I've had little issues with trying to get things. So anyway, I thought I'd just show some meteors. The other thing is I just really like meteors. They're probably one of the most interesting things I know about. So August is a big month for meteors. Of course, we just finished up with the Perseids. Actually, there's still a few stragglers out there. If you go out and look really late at night, you can still catch them out there. So there's a couple of other meteor showers that happen in August, and as we move into the fall, there'll be some others. So maybe worth just revisiting the meteor situation. So first of all, I mean, what is a meteor and where do they come from? Of course, we've talked a little bit about this before, but there's a sort of a confusion between what's a meteor and what's a meteorite, what's a meteoroid, that sort of stuff. What's a meteor wrong? And, meteors basically are just streaks of light, right? They're the atmospheric effect of something passing through the atmosphere and heating up, basically. So sometimes people talk about them, particles burning. They really don't burn. There's no combustion taking place. What's taking place is ablation. Like bits of material are superheating and coming off these things. And that's what you see. When you see that little streak of light, what you're basically seeing is little bits of stuff that have superheated and glow and leave this beautiful streak across the sky. And of course, that differentiates it from all the other funny things that pass through the atmosphere from time to time, like comets, which we hope don't pass through our atmosphere, but are significant because a lot of meteors are bits of material that used to be in a comet and now are basically left behind. Asteroids, these smaller rocky bodies, right, that we bits and pieces fall off of from time to time. These things are continually crashing into each other and making smaller bits, and occasionally some of those smaller bits come through the atmosphere. So there's actually meteors that are remnants of asteroids. And then meteorites are big chunks of stuff, and by big I mean big enough to actually pass through the atmosphere and make it to the surface. So somewhat different kind of thing. But the meteor really is just the streak of light. So the International Astronomical Union defines meteor as the light associated with the physical phenomenon of a solid object, which enters a gaseous atmosphere, usually at a really relatively high rate of speed, by which I mean a very high rate of speed, fast enough to ablate and burn up. So you get heat, shock, and ionization. A lot of what you see in that streak is ionized material, which we'll also talk a little bit about later tonight. And you see these shooting stars, and occasionally you see a nice fireball. I think the best one I've ever seen was actually during a Perseid shower when, I don't know, some years back I was teaching a field camp. I was actually teaching a field camp for KU. And the field camp was just outside of Canyon City, Colorado. So kind of a dark, remote, dry place. We went and a group of us went and sat out on the trash dump of this place and watched these things. And it was a year when there was a storm, so it was unbelievable. Just like probably at least one a minute for on and on and on. But we saw one that sort of, sometimes they take a longer path through the atmosphere and it's a larger object, and it was just amazing.
You ever seen one fall apart?
I've never seen one fall apart. I've heard about people talk about
Yeah, I saw it one time, and it was when I finally got my kids
it. Yeah,
and it just kind of sparkled.
so it worked perfectly in that case.
Mhm.
And so if you really look closely at these, you see that they have different colors, right? The color kind of tells you a little bit of something about the constituency of these things, because for reasons that have to do with chemistry and quantum mechanics, things that I don't really feel like I've got the mental gas to talk about tonight. When you start ionizing these various elements, right, they glow, they emit light in a particular parts of the spectrum. So calcium is kind of down here in the short end of the spectrum, blues and purples basically. And as you start getting more towards the reds, you start moving further out of the spectrum. Iron, magnesium, sodium, another form of nitrogen, and then oxygen. So these are all, you can kind of tell what one of these things is made out of if you had a spectrometer, right? Which we'll look at one here in just a second. You can actually see what the composition is. There's people, a lot of amateur astronomers, this is what they do, because this is the sort of thing that the professional astronomer really wouldn't be able to do, but volunteers with the right kind of equipment can do it pretty readily. So as far as how these things came to be, really what they are is part of the trail of something, usually a comet, that's passed through. So comets on a big orbit, usually kind of a big elliptical orbit, continually leaves a stream of stuff behind as it goes. It's like, I don't even remember Peanuts, the cartoon, Pigpen, the little kid that was always sort of needed a back, and he would always be depicted going along in this trail of dust following him. In some ways, comets and asteroids or smaller objects are kind of like Pigpen. They leave this trail of stuff behind them. And every once in a while, the Earth will pass through one of those trails of stuff. And when it passes through one of those trails of stuff, one of the bits of debris, that stuff starts coming through the atmosphere, and it becomes meteor showers. So basically what you're seeing is usually cometary, occasionally asteroidal debris that has sloughed off of one of these moving objects and is passing through our atmosphere. It's also why, the meteor showers tend to come from specific points in the sky. It's called the radiant. And that's actually how the showers are named, right? It's the constellation where they're radiant is. And that's because, you know, as the Earth passes through, that's in a particular part of the sky. So that's why you tend to see these things not just coming. I mean, some just randomly come from various directions, but the real concentrated ones come from a particular direction. So how big are meteors? Spoiler alert, not this big. This is actually a comet. This is the comet with two Russian names, Churyumov or something or other. Churi-Guri is what everybody ended up calling it. It's pretty big, right? That would be I think that's Denver in the foreground there. So this would be a very bad day in Denver if this were to ever actually happen. But I guess it's pretty big object. What makes a meteor is nowhere close to this big. It's really more like that. Relatively small bits of stuff, sand, grain, pebble size, very small. And yet they make all that light, right? Which tells you a little bit about the velocity that they pass through the atmosphere with. So they tend to be micrometeoroid sized bits of stuff. As far as the major meteor streams, of course, we just saw the Perseids, which peaked a couple of weeks ago, but every once in a while we're still getting a straggler, but they happen in early part of August. If you get 100 per hour on this, that's a little high, I think, but not completely out of the question. Depends on how late you want to stay up in a lot of cases, but they are the remnants of the comets with Tuttle. Before too long, we're going to get the Orionids, which originated in Orion, right, towards the end of October. They are actually remnants of Comet Halley, right? And so on. You can kind of see these are all from 2024 because that's the date when I made this slide, but they're about the same. So these are some of the major ones. There's a bunch of others though. I like the quadratids myself. They can really be spectacular sometimes. The problem with them is that they happen in the 1st of January, and it can be just mind-blowing cold to go out and watch these guys. But they can be an absolutely amazing stream. So mentioned the Perseids, which has been the most recent one, and so they're called the Perseids because they tend to appear from the direction of the constellation Perseus, right? This Perseus always looks to me a little bit like, I don't know if you guys ever watched the Jetsons, but the Jetsons had a robot named Rosie, and it kind of looks like Rosie the robot to me. But I don't know what it's actually supposed to be. Perseus was I don't know, some hero of some sort, right? But I probably should know my.
Well, and he cut off the head of Medusa.
Was that Perseus that did that? Anyway.
And
So.
that's supposed to be I've seen it drawn so that it looks like he's holding up the head of Perseus.
Okay, well, I mean, that's a much more heroic interpretation than Rosie the robot. But, anyway, and the Perseid radiant is right next to Perseus or Rosie's head, basically. And you would see if you were watching all this, you would be seeing these streaks of kind of originating from that direction. So that's one of the major ones. The Orionids, again, they're coming, and also kind of nice. Their radiant is up by Orion's Club, basically. So if you want to watch those, one of the things about most of these is you got to stay up fairly late at night too, if you really want to see them, or else get up really early in the morning, depending on how you choose to look at it. So anyway, those are a couple of the major ones. There's the Geminids. Geminids come from this body right here, which has actually been studied with radar. Right, so this is a radar image of Phaethon, which is a asteroid, and it's been determined that the Geminid meteor shower is material that came from this. It was determined by spectroscopically examining it. This was done at the Arecibo radio telescope in Puerto Rico, which is no longer there, right? Collapsed a few years back. I think they've completely removed it now.
Yeah.
There's just a bowl in the ground where it used to be. But anyway, it kind of stinks when your radio telescopes start collapsing and nobody wants to fix them. But anyway, All right, so I mentioned that it is possible to do astronomy with these, and there's a pretty strong interest group of people that are interested in this. If are you familiar with ALPO, ALPO,
Oh, yeah.
the what is
Yeah,
it?
what it means.
Association of Lunar and Planetary
Lunar and
Observers.
planetary.
The ALPO has a section on meteor astronomy that, if you're interested in it, and one of the things I was also thinking about doing a little bit about is talking about all the various astronomy societies and what they offer. But anyway, would be a kind of a typical rig for this. This, of course, is just some sort of equatorial mount with a power supply and stuff on. There's a camera right here, a video camera, and then on the front of that video camera is one of those diffraction gratings, a star analyzer, yeah, S100 or something, which is basically just a transmission grating, right? A transmission spectrum grating. It's a pretty simple thing, really. Costs a couple $100, I guess. Not particularly expensive. And you just point one of these things toward the radiant during the time and let it record. It gets,
We've actually got one.
yeah. And this is the kind of data that you can get from these. You can see all these little lines right here that represent magnesium and iron, sodium, and oxygen, nitrogen, and so on. So you get the idea of what these things are actually made of. This is going to be very valuable data, actually. This is very useful data to collect, relatively easy to collect. I mean, if we end up with gazillions of stupid things in the sky, this may be the kind of thing that can still be possible to do with, reasonable efficacy. So anyway, so it is possible to do optical astronomy of these. It's also possible to do radio meteor detecting. This again is something that is common activity in, particularly in Europe. There seems to be a group of people in France and a group of people in like Hungary that are very interested in this. And the idea here is that as one of these meteors passes through the atmosphere, it leaves behind this trail of ionized material, right? Which we'll talk about what that means here in a little bit. And one of the things about ionized material, plasma, right, is that it kind of affects radio waves. So radio waves will bounce off of these things. So if one of these passes through the atmosphere, it kind of basically makes a temporary little radio signal that can be developed, that can be detected with relatively modest equipment. So this is really just a little antenna that is tuned to about 50.5 megahertz. So the idea is that there's a transmitter somewhere, and this is not a dedicated transmitter. It's basically just a radio tower. And you tune your receiver to the transmission frequency. And then whenever one of these passes through it, it almost makes like a interference signal, right? Almost like static. And they record these things and submit them. And it's probably a little bit of an interesting way of passing the time. So anyway, it's possible to do some radio astronomy with these as well. Okay, that was all I wanted to say about meteors. Again, if anybody has any idea and they want to do one of these things, I'm more than happy to yield the word. Okay, so the other thing I wanted to talk a bit about tonight, more like the main presentation, actually came about. The question kind of came into my mind from reading as usual. And I read this story where astronomers had discovered a brand new type of astrophysical object that they were calling a black hole star. Did anybody see this or have been following this story? So here's an article that they wrote about it. It's basically kind of an enormous star with a black hole in the center of it, and it's never been seen before, and mysterious stuff. And it sounded pretty interesting, but what it really got me thinking about was, what really is a star, right? And it seems at first like a fairly obvious question, right? I mean, we know what a star is, right? The sun's a star, all those things up in the sky, they're stars. Stars are in some ways almost overlooked objects. I mean, you ask somebody like, somebody with an interest in astronomy, what's your favorite type of object? Rarely ever does somebody say, well, I really like stars. It's always like, I like globular clusters, which are stars, but I like galaxies, which are stars, but a collection of them, or planetary nebula, or some of these, people rarely ever photograph a star. because they're just not that photogenic, right? So stars, I think, tend to get a little bit overlooked, but astronomy, if you look at the word, it means naming stars, basically. So yeah, so it just got me thinking a little bit about, what is a star? And so I thought I would look into it in a little bit more. The other thing that sort of got this rolling around in my head is, and I mentioned a little bit ago that it's been 20 years ago now since this debate sort of reached its head, but for a long time, people have debated on what is a planet, right? And again, it's one of those things that I was learning astronomy back in the 70s and 80s. It's like, well, planet, it's a planet. And, it's a star. And there really wasn't ever a formal definition of a planet for a very long time. Some would maintain that there still isn't. But it was this debate that became rather widely known. I mean, it's one of the very few scientific topics I've ever heard about that escaped from science and got out into the public, and so people were interested, like, what is a planet? But I don't think there's ever really been a similar sort of thing about stars. And of course, what is a planet has become an even more interesting question because, people debate whether there's 8 or 9 planets. Well, there's thousands of them, and most of them are not around our sun. Which brings me to, my point, and I have one, which is that all of these planets, they're orbiting around, well, I won't say all of them because there's a few rogues out there that are just drifting aimlessly in space, but for the most part, these things are all around stars, right? So I figured I would just spend a little bit of time thinking of what is a star? So here we go. So first thing I did was look up a formal definition of star, and lo and behold, the Hubble Space Telescope, or the Hubble Science Institute, the NASA ESA joint institute that runs the Hubble, thoughtfully made this slide with a definition on it that's pretty similar to the definition I remember learning somewhere back in or so when I was taking astronomy classes. A star is an approximately spherical body of plasma held together by its own gravity and prevented from collapsing by energy generated by the fusion of hydrogen into helium. So that's it, right? We can stop now. Okay, we know what a star is. It's 8 o'clock. We can all go home, right? Well, we could. I mean, if you guys want to, I'm certainly can't stop you. But let's think about this definition here a little bit, because there's stuff in here that it's like, okay, what do you mean by that? Two things here that really kind of stuck out in my mind is plasma, right? Because, back when I was a starting college student, I used to donate plasma in order to make money, and I'm pretty sure that none of that ended up being in a star. So plasma must mean something more than just that stuff that they take out of your veins when you're starting as a college student. And fusion, right? So one of the things that would be readily apparent to me about this definition is that prior to any understanding of what nuclear fusion is, which probably came about in the 1920s, maybe it's been about 100 years since people really started understanding, or at least beginning to understand it, you couldn't have defined a star in these terms. Now, I don't really know when plasma as a state of matter first was recognized. I don't know, Ed, do you know? But I'm be willing to guess that it was not really that long ago on the time scale of human thought about stars. So this has got to be a relatively recent definition, and by relatively recent I mean, would not have made any sense to somebody 100-ish years ago. But and yet people were talking about stars way before all of this, right? So what is a star? The ancient version. I mean, there's been all these speculations down through the years. There was this whole mythology that developed around stars. One idea was that stars were like, there was this big circle or this big sphere of surrounding the earth that had holes in it, right? And then beyond that, there was some dark or some bright material, and the light shining through was in, you know, it's probably for the time that people were speculating on that, it was about as good a guess as any, really. There were people already beginning to realize that there were these objects in the sky that didn't move the way stars did, that they called them wanderers, which became planets, right? Planetes. So it's been a question probably that people have thought about for a very, very long period of time, but really without the context to really understand it. Of course, there was this thought then that the Earth's at the center of all things, right? And all this stuff is kind of moving on us, which we kind of understand is no longer the case. Scientific thought about stars actually goes back a little bit further in time than you might think. One of the first people to realize that that stars were something similar to the sun was Giordano Bruno, who lived in the, I guess, mostly 16th century. Ran afoul of the religious authorities of his day for speculating about this. I think he was burned at the stake over this, so did not end well for Giordano. But his thought was that basically a star is something burning out of space, which again is kind of closing in on the answer. The problem is, what is burning out there? And there were speculation there were like coal or something like that, which probably became relatively clear early on that probably couldn't be the case, but nobody again really kind of knew about any of this. One of the people that sort of made some fairly significant progress on this is Lord Kelvin, right here, whose name is not Lord or Kelvin, but I can't remember what it actually is. But this guy was, you know, one of the most prominent physicists of his day. He tends to get a little bit of a bad rap for his thoughts on what stars were and what made them work, but he was actually one of the, you know, leading physicists of his day. And his idea was that stars and the sun in particular worked by essentially gravitational contraction, right? The gravity, you know, by now he's realizing that this is a ball of some sort of matter, that the gravitational forces are shrinking, and as they shrink down, that generates heat. And this came about from a realization that combustion could never have really produced the distribution of light that we see from stars, right? And again, this is a guy in the late 1800s that was doing this, so we're talking sometime back in the past. So he was basically able to dismiss the idea that it was combustion, it was chemical burning that was producing this. The problem is, and he was very forthcoming about this, he did not try to sugarcoat this in any way, is in order to generate enough energy from the mass that you could measure, and again, you could measure the mass of the sun by seeing how it makes things move around it, that it could only be about 20 million years old. And at that time, it was already understood that the Earth was considerably older than that. At that time, the speculation based on geological evidence was the Earth was about 1.5 billion years old, which is off by, it's about 4.5 actually. But still, it's a way longer period of time than 20 million. So, you know, Kelvin was pretty forthcoming about this, that, you know, this probably was not the mechanism that was actually played here, because it resulted in a sun that was too young to have had the Earth, at least the way we thought of it. But it was a viable way of thinking about what the star actually was, right? The breakthrough, and the thing that makes the modern definition work in a sense, or at least be viable, was in the 1920s when the idea of nuclear fusion came into play, right? So nuclear fusion, pretty simply, is exactly what it sounds like. Fuse together, you force together elements at very high temperatures and pressures. And it has to be fairly light elements in order to fuse them, and they produce heavier elements and energy, and a lot of it. And this all came about from theoretical work in the 1920s. Probably the leader of it all was the guy in the middle here, was Eddington, right? Eddington was one of the first of these scientists to think about this idea as happening in stars, right? I was listening to just yesterday when I was going to get my car, I was listening to a podcast, and it was two professional astronomers, and they were talking about stellar evolution and stellar things. And one of them said something that was really kind of stuck with me. It said that in astronomy, and again, I'm not a physicist, so I can't really comment on this personally, but it's often the case that observation leads theory. That we observe something, in the particular case of the sun, we observe the fact that it has this temperature that can't be accounted for by standard combustion, right? Something else has to be happening. But nobody really knew what, right? And so the, effective temperature of the sun was probably measured in the 1880s. 40 years later, well, no, that's probably too little, maybe around the turn of the century, right? The last century. 20 years later, now nuclear physics is starting to catch up, and there's come to an understanding that maybe what's happening in the interior of these stars is this nuclear fusion process, right? And these are some of the people that I probably one time, that's Ernst Rutherford right there. Eddington, that's, oh gosh, the guy whose name starts with, shoot. Anyway, I'm sorry. Not coming up with the answer there. But anyway, these are all the physicists who were kind of working on this alpha, all kind of working on this theoretical idea about how all this might work. So that's a little bit of a history of, how the definition of the processes of stars might have developed. But I went through all that because now if we take a look at this definition, we maybe have some context to understand what it's a little bit better, what it's actually trying to tell us, right? So again, just to kind of point out a few things, it's an approximately spherical body of plasma. So there's matter held together by gravity, enough gravity that's forced it into a spherical shape, which happens largely because of the way mass works, right? Powered by fusion, mainly of hydrogen into helium. So the lightest element in the periodic table gets fused together to make the second lightest element in the periodic table, and energy. So if we now kind of think about what this might really be telling us, maybe we have a way of defining, understanding this definition of star. So first of all, what do we mean by plasma? All right, and again, I kind of alluded to this earlier, that this is a bag of, plasma is the part of your blood that's not the cells, basically. And you probably know this. And, again, as a student with, wanting to eat, I would sell plasma. Basically, you would go to these plasma centers and they would suck some of this stuff out, and they would send it to a centrifuge to get all the platelets out of it, and then they would shoot the platelets back into you and keep your plasma, and you got like $5 or $10 or something like that. This was back in the 80s, so I don't know what it is now, but that's a type of plasma. In the physical world, plasma is a state of matter where the electrons have been disassociated from their atoms, right? So if you think about the typical phases of matter, right, the ones you tend to learn in Chem 101 are solids, basically stuff that's held together in a rigid crystalline structure, right? That's really kind of the lowest energy state. And then there's liquid, where the bonds that hold these together kind of change their nature. They go from being covalent bonds, sharing electrons, to more like electrical bonds, a little bit more like magnetic attraction between them. So they can move around relative to each other, kind of slip and slide relative to each other. So it's liquids. And then there's gases where the molecules are completely disassociated from each other and move freely. And that's a step higher. And then at very high temperatures, like in stars, you can atoms start losing their electrons. So a plasma is just a mixture of electrons and nuclei disassociated from each other. And that thing that I showed you there, that's a plasma. That's in one of these little balls that you can sometimes buy in novelty stores, and basically they just kind of heat things up enough to make this disassociation happen. Plasma is considered a state of matter, but it's a kind of a different state of matter. One of the things about it is that it'll conduct electricity. A plasma will actually conduct because it's a bunch of loose electrons, right? So you can get a stream of electrons to flow through it, which gas will not do, right? So different from gas in that perspective. But the key thing here is you got to heat up stuff very hot in order to turn it into a plasma. By the way, practical understanding of plasma is pretty important, because if we're ever going to have nuclear fusion, it has to be contained within sort of a plasma bottle in order to keep from either melting or exploding everything around it. So the practical understanding of plasma is kind of a big deal. The other thing about plasma is really common. I had no idea. I knew there was a lot of plasma, right? Because all stars basically are plasma, but are largely plasma. I didn't have any idea that about 99% of visible matter is plasma. I would have guessed maybe 50, 60% if somebody had asked. 99%. Neon signs have plasma in them, and so do whatever these things are. Fluorescent lights, right? They have basically you send electrical charge through a bunch of gas, right, and it disassociates. One of the reasons why neon works really well for this, it's a noble gas, right? Its outer shell is full, and so it can dissociate those electrons a little bit more easily, and it produces these beautiful colors, right? And then lightning is plasma, and the stuff that makes up stars is plasma. As I mentioned, being able to harness plasma is one of the trickier technological feats that humans are trying to do, but also a pretty important one, because if you can create a plasma container, you can contain a fusion reaction. And if you can contain a fusion reaction, that would be a tremendous source of energy, right? That would solve a lot of, we wouldn't need windmills and solar panels and nuclear reactors, fission reactors. The joke has always been that, fusion is the energy that's always been 20 years away, because, you ask somebody, how long do we have fusion? It's always been 20 years. And it's been that way for quite a while now. But if people ever figure out how to do this, it will be quite a technological breakthrough. Of course, the downside of failing to do this is pretty serious, because we have actually been able to do nuclear fusion here on Earth, but they're bombs, and not just bombs, but very, very powerful bombs, right? So, you don't want to, you want to fuse without exploding, basically. But anyway, enough about harnessing plasma. So that tells us something about the plasma bit here. So, you sometimes hear people say, well, stars are big balls of gas, right? They're not. They're big balls of plasma. And, I don't know if you've ever heard the song by They Might Be Giants about the sun is a massive incandescent gas. Well, it's really not. It's a massive plasma. So, anyway, so that's the bit on plasma. What about the fusion part of all this? The part that was really the sort of critical scientific understanding. Well, if you think about this, then, go back and sort of make a picture of this definition. What we have here is a ball of stuff that's in hydrostatic equilibrium, which basically means that it's more or less formed itself into a sphere, right? That sphere is maintained by a balance between the force of gravity, which is a force associated with any kind of mass that tends to hold this stuff together, and then fusion, which is producing the energy, is pushing out. So the reason why stars kind of stay the way they are is that they're in balance between some types of stars. Really, the balance is a lot more complicated than that. Like Cepheid variables, like Polaris, is what's called a pulsating variable star, right? It gets bigger and smaller, bigger and smaller. And what's happening there is that in its outer layer, it's the layer that can basically trap this energy, I guess for want of a better word, absorb it, changes with temperature, right? So when it shrinks up, its physical nature changes and it becomes opaque to that energy, right? And so it starts absorbing it and expands. And then as it expands, it cools off and it becomes more transparent and it shrinks back down in this pattern of shrinking, expanding, shrinking, expanding. That mechanism, by the way, is called Eddington's valve, is what powers these pulsating in various forms of that, or what powers pulsating variable stars, right? But in general, this is, to a first approximation, what's happening in the interior of a star. So in order then for something to be a star, it's got to have this fusion taking place. And you would think, okay, so now we have accounted for what plasma is, we've accounted for what we mean by fusion. Are we done yet? And unfortunately, the answer to that is not quite. There's still a little bit more to the story, right? So here's a more detailed definition of stars, of a star. A star is a nearly spherical body. It's nearly there because some of them have weird shapes, right? And some of them are like expanding and rippling and doing all kinds of odd things. With sufficient mass to have core pressure and temperature great enough to cause the fusion of protons, right? A proton is basically just a hydrogen nucleus, right? It's a ionized hydrogen, right? It's hydrogen that's electron has been taken away. Into deuterium, which is another form of hydrogen, a hydrogen that's got a neutron in its nucleus. This is the key part, in a sustainable reaction. So this is a little bit more wordy definition of what a star is, but probably a little bit more accurate. So just to introduce you to a few characters in the thing here, these are the various isotopes of hydrogen. Protium is the most common hydrogen isotope. It's just a proton and an electron, right? It's the simplest form of matter. You strip off that electron by making it a plasma, and you basically just have a bare proton, and that's really what a hydrogen nucleus is. Then there's deuterium, which is proton, electron, and then one neutron, right? So it's an isotope. It's a mass variation. And then there's also the stuff called tritium, which is two of these. And you have to have fairly high temperatures in order to get tritium to form. All right, so with this in mind, can we sort of tweak our, now kind of put this to rest and say, okay, we've finally got to the bottom of the problem? Well, not quite, because there are things out there called brown dwarfs, which actually have at least part of the fusion process happen, right? So brown dwarf is an object that were first speculated on theoretically and then have now been observed. There's something that's not quite a planet, but it's really not quite a star either. And what's powering a brown dwarf is this fusion of protons, right? So we got two protons. This is the beginning of the first thing you learn in an astrophysics class, which is the PP chain, the proton-proton chain, which is the major power mechanism in the interiors of stars. So we take two protons, we squeeze them together under temperature and pressure. They produce a deuterium, right? A proton with a neutron associated with them. So that's deuterium right there. And an electron and a neutrino, right? And neutrinos are just these weird little elementary particles that pass through everything, right? The only reason why we know neutrinos actually exist, this is one of those great ironies, that one of the proof of all this, that one of the things that sealed the deal that what was happening in the interior of stars was some form of fusion, was that we were able to detect neutrinos on Earth, but we didn't go up into space to detect them or build telescopes on the surface. Where was it done? Anybody know? Deep mines, right? Down in the, isolated from all these other sources of radiation. There were big tanks of what basically is cleaning fluid, and you could detect neutrinos that way. So that's what really sealed the deal, that it was fusion that was happening. What's wrong with this picture though, other than, it's complicated physics and it's Thursday night and our brains are tired. What's wrong with this picture is this is not a sustainable reaction, okay? This happens and then you end up with a deuterium and that's the end of the story. So brown dwarfs are making deuterium like crazy things, but they are not, it's not sustainable. Okay, so sooner or later when they run out of hydrogen, when they run out of tritium, when they run out of just fundamental hydrogen, they're done. Okay, so if you want to sustain things, if you really want to be a star as opposed to a brown dwarf, the reaction has to be sustainable. In order for that to happen, you got to do that little bit that we just saw, right? This first part, but that's really just the first part of this proton-proton chain reaction, the PP chain. So here's that bit that happens in cooler, lower mass objects like brown dwarfs. In order to sustain this, you got to be hotter and you got to have more mass. And if you're hotter and you got more mass, then these deuteriums that are being created will further fuse with another proton. That's why this is called the proton-proton chain, right? Because we get proton fusion, and we get more proton fusion, we get creation of more neutrinos and gamma rays and all this other subatomic particles that are detectable. And you eventually end up with a couple of light heliums, right? Which also fuse together. So see, if you follow the players here, right? We got hydrogen, hydrogen becomes deuterium, fuses with hydrogen, becomes helium, right? So the next heavier element in the periodic table, but a kind of a heavier form of helium. And those two fuse together and we are back to a final helium and two hydrogens. And this is why it's sustainable, because these two hydrogens can then go back and become part of the PP chain again. So this is a sustainable process. And that's what really distinguishes the type of fusion that's happening in a star from the type of fusion that's happening in a brown dwarf. So if you want to think about this as kind of a continuum, this is another way that it can happen, right? Bigger, heavier stars can also have what's called the CNO chain, which is a catalytic chain, actually. It's a little bit more to it, basically, but it still basically involves the fusion of hydrogen with helium, and it's a sustainable process. By the way, the CNO chain was theoretically proposed, but not actually observed until not that long ago. It was sometime in the 80s that it was determined that the CNO chain was actually happening, and it was due to measurements of some of these abundances of gamma rays and neutrinos. So back into, going down into the bowels of the Earth to detect all this stuff. And it was thought that probably the CNO chain was dominant in heavier mass stars. Turns out that it's actually a little mix of it. So even a star like the sun, which is, one solar mass, basically, can have a little bit of CNO reaction taking place, but it's dominated by proton-proton chains. As you start to get into heavier stars, a little bit more weighted toward the CNO. The key point, again, to kind of take us back to our definition is these are sustainable reactions. They continue on. So if we want to think about this as kind of a continuum of matter, right? If you've got matter that's not dense and hot enough to do any sort of fusion, basically you're a planet. Maybe that's how we should define planets, right? A planet is anything that doesn't have fusion taking place. That would probably open up an even bigger can of worms, because that would include everything that's not a brown dwarf or star, but it's at least worth throwing the idea out there. So up to about 13 times Jupiter's mass. So something that is up to about 13 times the size of Jupiter will still act like a planet. It won't fuse. It may actually emit some energy. I mean, Jupiter emits energy, but it's not due to fusion. It's due to chemical processes, basically. And then if you're between about 13 to 80 times Jupiter's mass, that's a brown dwarf. That's an object that's doing fusion, but not in a sustainable way. So it's kind of a middle range. And then about 80 times Jupiter's mass, that's enough mass to do fusion in a sustainable way. You're off to the races. you're a star. So one of the things that this kind of implies is that the stuff that becomes a star was something before it was a star, which kind of suggests something about the basic nature of stars, right? That they don't just appear magically; they come from something. And we've talked a little bit about what how this happens. I think we've discussed this in past meetings. Basically, you get these clouds of gas and dust, proto materials, right, that get disturbed by gravity or nearby actions of nearby objects, and they start to stick together. At first, they stick together kind of electrostatically, right? They're kind of magnetically attracted to each other, and then as they get more massive, it becomes mass attractions, and eventually they get big enough to start attracting even more clumps and even more clumps, until eventually you get massive enough to have the initiation of fusion. And then again, that's at the point where these things become stars. So just to kind of complicate things even more, though, here's a kind of another view of all this. This apparently came from the Science Photo Library, and I couldn't get rid of the watermark, so sorry about that. I'm probably violating some kind of a copyright here, but anyway, there's a bunch of different kinds of stars, right? We all know that stars are not just stars. So what's up with that, right? And this is not really about how stars behave during their lifetime. I mean, we're really trying to understand definitionally what a star is, but we need to kind of come to at least some understanding of what of the various types of stars, because that really bears a lot on the issue of when is a star not a star anymore, right? There's a state of matter before stars, and you can kind of see this happening. There are objects out in space that are probably stars in the process of forming, but they're not quite there yet. And then there's certainly a whole bunch of stuff out there that's what happens after the star is not a star anymore. But there's several different pathways that these would follow. It basically boils down to mass, right? If an object is above a certain number of solar masses, its fate will be rather different than stars like the sun, which usually end up in a somewhat different state. And that's what this is all about. So heavier things, right? Larger stars eventually become even larger, hotter, become larger, hotter stars. They live shorter lives, and their ending is usually a little bit more dramatic. They explode, basically, and then form these sort of leftover things. But somewhere in here, they make the transition from being a star to not being a star anymore, all right? For the branch of stars like the sun and up to about 1.3 or 1.4 times the mass of the sun, they can still go through this kind of giant phase, but they end more with a whimper. They become white dwarfs or planetary nebulae, but they sort of end up at these places by the process of not being a star anymore. So the formation of stars is a little bit of a interesting story. They kind of have this sort of period where they're kind of not just made the transition, right? And one interesting type of star that is actually a star, it meets the definition, but it's a really new star, is what's called a T-Tauri star, or a Tautari star. These are a type of variable star, relatively cool enough to actually have molecules in them, right? You know, you have to be relatively cool to have molecules, because molecules come apart under heat. But they still meet the definition of a star. So these are kind of weird objects. But they're stars that have just gotten going, and they tend to be surrounded by clouds of stuff that's kind of the leftovers from their birthing process. So these are interesting things to observe. I belong to the AAVSO, which a couple of you also do. And there's a pretty active group in the AAVSO that observes these things, because there's really a lot to learn about them. They're not extremely well understood. So the key to understanding stars, of course, is the Hertzsprung-Russell diagram. This is something that gets burned into your brain if you ever take a class in stellar astrophysics. I mean, in some cases, almost literally burned into your brain, because it's really the key to everything that I understand. One of the things about this is that stars move around on the Hertzsprung-Russell diagram. And that's sort of implied here, right? Because you can see we ended up with a blue giant that became a red supergiant. So if we look at that, right, the blue giant stars are all up here. They're very hot. The Hertzsprung-Russell diagram is a diagram formed from the absolute magnitude, or the luminosity, right? How bright the star is, intrinsically bright it is, and how hot it is. So this is hot down here. This is 30,000 kelvins. That's extremely hot. This is about 6,000 kelvins. That's about what the temperature of the photosphere of the sun is. And we get to cooler ones right here. Surface temperature of the Earth is roughly 350 kelvins, just to put that into perspective. So we're talking super, super hot here, right? And stars that, and I used to think, and I don't know exactly why I thought this, but you know, things move around on this. So typically a star will move, and I, for some reason, always had it in my mind that stars moved up this bar, right? This is called the main sequence, right? This is where stars essentially are born on the main sequence. But it always, for some reason in my mind, that you moved along the main sequence. That's really not where stars are kind of born onto the main sequence, and then as they pass through their life, they move off of it. So this would be the typical trajectory of a star like the sun, right? So the sun is a star like it is on this, right? It's a G type star, sort of a middling temperature, middling mass. So a star like the sun, as it starts to exhaust its nuclear fuel, uses up all of its hydrogen, starts burning the helium. And I use that word burn there with an understanding that we're really not talking about combustion here, we're talking about fusion, right? And as that happens, the star starts cooling off and getting bigger, so it becomes a red star, and it sort of moves off into this red giant area of the Hertzsprung-Russell diagram, until eventually it, you know, goes through all these iterations of burning hydrogen and burning helium and using up its hydrogen and eventually using up its helium, and it ends up being a thing called a planetary nebula, right? Which is just the former mass of the star expands, right? And then as the force, that outward pressure decreases because fusion goes away, that part of the star shrinks back down, becomes this white dwarf, and that stuff that gets left behind, that bubble of stuff, is a planetary nebula. So that would be at that point where a star like the sun is not a star anymore, because it's no longer has any kind of fusion taking place. There's still a little bit of ambiguity in all this, because at some point in there, there's still going to be helium fusion going on. So is that strictly the definition? I mean, is it that when it stops being a star? I really don't know the answer to that. If we had a real astronomer here, they might be able to help us with that. But clearly there's a time where the thing that used to be a star is not anymore. And higher mass stars, lower mass stars born on the main sequence become red giants. Higher mass stars become red supergiants, and then eventually they go through a much different sort of fate as those hydrostatic pressures cease. They collapse, but they collapse in a big hurry. Like the entire star collapses literally within hours, and that collapse produces a resumption, a very rapid resumption of fusion, which happens again very fast, and it's an explosion, so it blows all that stuff back out, and you end up with these supernovae. And then the remnants of those are neutron stars, the last little bit of the mass that made up the star, and in some cases a black hole, right? It becomes so massive that it essentially traps all light. But at any point, there's a transition in here where the star is not a star anymore. All right, so the larger stars, as I said, they sort of end with a bang, right? We end up with these sometimes rather beautiful objects, right? Supernova rings can be really important. Planetary nebula are quite beautiful objects as well. Smaller stars, bigger stars, they go out with a bang. Smaller stars go out with a little bit more of a whimper, but they can make some pretty beautiful objects themselves. I've always thought planetary nebula are really gorgeous things. But at this point, it's pretty clear that these are not stars anymore. They are what happens after a star. But as with many things, the end is a beginning. The stuff that is left behind when a star is no longer a star becomes raw material for the next generation of stars. And in fact, we know that this has happened on a pretty large scale, right? The oldest stars, if you look out at the old, very old stars, like stars of globular clusters and things like that, they are metal poor stars. In astronomy, a metal is anything heavier than helium, right? And so these are metal poor stars that don't have many heavier elements. And those are an older population stars. They're called population 2, but they're the older stars. And then population 1 stars are more metal-rich stars. They have more heavier elements. And there's actually, it's thought that there's even some population 3 stars, even older ones, out in the galactic nuclei, basically. So this is all part of a big recycling process. So, sooner or later, all of the atoms that make up everything, including us, are going to go through all this process and get recycled. And somewhere in the unimaginable future, will become part of new stars, basically. So there's those populations, right? Population 1 existed about the time of the Big Bang, early universe, right? Tend to be very low in metals, right? Older stars, low in metals. Population 1, so I don't know why the numbering system seems a little screwy to me. Newer stars have smaller numbers, but anyway. So much more metals, 1 to 3% metals in this case. So if you look up stars in a catalog, a lot of times, if it's a technical catalog, you'll see their metal content given, and that's a somewhat indirect measure of how old the star is, among other things. All right, so that's it. That was my quest to figure out, or to find out, or to finally know what a star actually is. And so I think,
Well, I've known about all this kind of stuff. There's a lot more detail. I know it's kind of, the way you did that there was kind
yeah,
of neat.
yeah.
Too, brown star when it runs out of fire.
What happens with the brown dwarf when it runs out of fire?
Yeah.
I don't really know.
Yeah, brown, whatever, what was that, we call it?
Brown
star?
dwarfs.
Brown
Yeah.
dwarf.
My guess is they probably would just sort of collapse, right? Because the mass would still be there,
Yeah,
but the pressure
yeah.
would not. So my guess is they would just kind of collapse.
Well,
But that's actually a really good question. I don't know the answer. I'll look that up, maybe get back to you. I think brown dwarfs have actually been observed. They were sort of a theoretical idea when I was taking astronomy classes. They would talk about them, but I don't think any had actually been observed yet. I think since then they have. They're kind of faint. They're not easy. They're optically, they don't really show up. So they're typically observed with millimeter band telescopes, right? Right, somewhere in the fuzzy region between optical and radio. All right, other questions?
And they're not brown dwarfs.
That's a really good. That's a good question, Wes. I honestly don't know the answer to that.
While I'm waiting for the blood moon, I might just look that up. I might Google that.
Yeah, I'll be curious to know.
See what
Actually.
Dr. Google says.
But yeah,
Yeah, I think they said this is like 97%.
Yeah.
well,
I've taken a picture of the last one. So we'll see.
I hope I am able to stay awake, but I wouldn't bet large amounts of money on that. Like I said, this has been a rough week. It's not even over yet. Okay, so as ever, if anybody wants to